So we'll get started. So it's my great pleasure to be able to introduce Ezekiel Johnston-Halperin, or Zeke, as he's known, to give a PQI seminar this week. So Zeke was undergrad at Case Western, and then he joined the PhD program at UC Santa Barbara, where we did not overlap. Do you? No, probably not. Okay. And he worked in the group of David Aushalom. And then after working there, he joined the group of the Jim Heath group at Caltech. And then you were assistant professor in when did you start? In 2009? 2010? Six. Wow, yeah. So time flies. Yeah, so Zeke has actually has worked in a number of different areas. The one that I asked him to talk about today is I think is really quite fascinating. Of course, the other ones are as well, but I think this is really amazing organic materials that behave better than best known ferromagnetic spin wave materials that are commercially used, and there may be some future quantum applications, and he'll be telling us about that as well. So thanks for coming.
Thank you for that nice introduction, and this has been really a great visit. So you guys had a lot of really exciting stuff going on, and really enjoyed the warm welcome and the fun conversations. So as Jeremy said, my group covers a couple of different areas of research. And in principle, there's supposed to be some sort of synergy and organization to this diagram. It sometimes works better than others in that sense. But today, I'm going to be focusing mostly on these new magnetic materials. And that touches on magnetization dynamics and nanoscale phenomena as well, but sort of the push, if you will, is from the new materials direction. Because I always run out of time before giving this slide at the end, I want to thank everybody who actually did the work up front. These are all current and former graduate students from my group, including one sort of pending former graduate student, and people who are looking for a postdoc. This guy is really top rate and has done some of the work you'll see here. And we also have a lot of input from external collaborators. Any project like this takes a lot of hands pulling together. So I want to start and talk about sort of just generally one of the reasons why you shouldn't be afraid of organic materials. So I know, my background is solid state physics, and you talk to most people from that field, and you get some sort of allergic reaction when organics come up. But I just wanted to point out that this is not all sort of either mysterious squishy physics or completely useless proof of principle. So organic semiconductors are making big inroads in technologies, most notably in displays, but also potentially in electronics as well. But if you sort of compare this portfolio to inorganic materials, spin and magnetism is almost completely lacking. And one of the reasons for that is that finding an appropriate organic-based magnetic material to complement, to make flexible displays is a challenge. I think the material we're going to be talking about today has potential here. We're certainly not going to be talking about anything this far downstream, but just to point out that this is a big gap in existing application space that the organic materials and magnetic organic materials have the potential to fill. So I want to spend some time now sort of introducing this material because, as I said, it's unconventional by most solid state standards, and probably many of you have not heard of it before. So after extensive chemistry training, I can pronounce vanadium tetracyanoethylene, TCNE, or VTCNE is the name I'll be giving it throughout the talk. So the TCNE molecule is this blue H shape here, where these lighter blue atoms are nitrogen groups. So that carbon-nitrogen is a cyano bond. And this material forms as a bulk material. So it's not a polymer, it's not a small molecule. It's coordinated through these vanadium. So every vanadium connects to 6 different nitrogen groups. And then vanadium can talk to vanadium through the molecular orbitals of this TCNE. So through various structural characterization techniques, this local ordering around the vanadium is very well defined. So it's not amorphous, it's not random, but long-range structural order is harder to identify. And I'll come back to that later in the talk, but for now, we can think of it as either somewhere between amorphous and polycrystalline with very small grain size. In addition to sort of making an electrical connection here as an organic semiconductor, allowing hopping transport throughout the material, you also have an exchange interaction whereby the vanadium, which starts off with 5 electrons, donates 2 charges to the neighboring TCNE, giving them a negative charge and an excess moment. So then you end up with antiferromagnetic ordering locally between a TCNE and a vanadium, or ferromagnetic ordering globally. So this is a compensated or imperfectly compensated antiferromagnet. So you have some remnant moment. You can just do it by counting. You have 3 electrons on the vanadium pointing one direction. The 2 electrons that get kicked off into the pi star orbitals of the TCNE point in the opposite direction. So you're left with 1 net Bohr magneton per formula unit of magnetization.
One quick question. So
Yep.
so there's a paper that you're citing from 1991.
Yep.
High profile.
Mm-hmm.
Presumably this beast TCNE. So do people forget about it, or like what's going on?
That's an excellent question. So this is one of these questions of science sociology that I'm not sure I have like a clear answer for. I can tell you sort of my best guess is that the synthesis is medium hard for a chemist. So it's not easy for a chemist, which would make it barely accessible for a physicist. So there's some energy barrier to getting into the field. And a lot of the materials properties that I've been selling as I've wandered around today were not evident in this first publication. So the Curie temperature in that publication was, I think, around 400K, 350 to 400K. And the material uniformity was not as good. And also a big part of it is sort of if you compare this timeline to the timeline of inorganic spintronics, it wasn't clear what to do with a magnetic material in 1991. So some of this is just sort of an idea before its time, and then other fields catch up, and sort of some of those synergies become apparent, et cetera. So we can maybe come back to this in a couple slides when I provide a little bit more context, but that's my best guess, yeah.
Why isn't that thing Jan Teller to start? It's got all that degeneracy.
So
usually when things have degeneracy, there's a possibility of distorting the Jan Teller effect and removing the degeneracy.
To
the T2G with the 3 spins on it.
Why are those 3 spins still energy degenerate?
Why is Teller to start and do something?
I don't know. So this is not a model we developed. This comes out of sort of these references. So I can tell you that this math of getting 1 Bohr magneton per formula unit to within the experimental accuracy is borne out. So if there's symmetry breaking here, it's not suppressing the magnetic ordering. I will say, in my opinion, the charge transport in this material is not well understood. So it's in this regime of many organic semiconductors where you can think of it as either a pretty good hopping transport or a pretty terrible band transport. But it's also potentially ambipolar. So if you So this is what this is supposed to indicate, and again, some of this is sort of received orthodoxy from prior people in the field, and we're still in the process of sorting out how much of this we believe and how much we don't. But if you want to call this the HOMO and this the LUMO, is the pot. So the conduction band effectively sits on the TCNE sites, and it's in this pi star orbital, but it's energy shifted from this state by the Coulomb occupation energy. And then exactly where these T2G orbitals sit in this gap is a little bit of guesswork. So you can do sort of thermal activation measurements and you get an activation energy of 1/2 an eV. So if you believe a simple band model, then that's where this comes from. But if it's a hopping conductor, then that activation energy means something different. And so conventionally, the solid state physics way to resolve this is do a careful temperature dependence and do log-log plots. The challenge here is that this material is deposited at about 350 Kelvin. That's where it grows, so you can't make it much hotter than that without decomposing it. And if you cool it down, the carriers freeze out by about 150 Kelvin. So that's just not many decades of temperature to get a reliable fit to sort of do some of these power law analyses and say, well, this really is hopping, this really is band light, this really is whatever. So it's not a direct answer to your question about why it wouldn't, but I'm an experimentalist, so I guess saying from the experimental point of view, understanding what are these states that we can measure, that's I guess the closest I can get. They are somewhere in that gap. they're at least not quenching the magnetic order. Talking a little bit about how this material is grown, I said it was sort of medium hard. The thing that makes it medium hard is this is not a commercially available reagent. So this VCO6 we have to synthesize ourselves, and it's the kind of thing most chemists would be able to do, maybe with a little bit of practice to get it right. The TCNE is commercially available, but once we have those compounds, we basically just put them into the inlets of this reactor. We use argon vapor phase transport to bring the precursors into the reaction zone here, and set the substrate temperature independently from the precursor temperatures to sort of control the stoichiometry and deposit. And so we typically operate, as I said, 50 C or 350 Kelvin, depending on how you want to look at it. It's ambient pressure in a glove box, so a little bit above atmospheric pressure, and seems to deposit on pretty much anything that's reasonably clean. So it doesn't seem to like substrates with organic solvent residue or that are dirty. Sometimes it won't deposit, but anything that is a sort of reasonably clean surface, it seems to deposit on. And so one of the things that I've also been saying as I talk to people throughout the day is I think this material system is heavily undersubscribed. And so very happy to share everything we know about how to make it, if anybody else is interested in, or to share samples if that's more appropriate. But in the first instance, we sort of had a fun experiment here. I don't know if anybody else has ever even heard of this journal. When they contacted us, this was the first I'd heard of it. It's the Journal of Visualized Experiments. So you can actually go see the 15 minutes of fame of my graduate students videotaping the synthetic process and sort of the full synthetic recipe about how to generate this material. So that's how we produce it. That's a lot of buildup. Let me start talking about why I'm here and why I think you should care about it. So this is the hysteresis and the temperature dependence of thin film deposited on, I think in this case it was probably glass. And coming back to Jeremy's question, this is the 1991 paper, which was powder derived from a solution phase synthesis around 96, just before 2000, the first CVD synthesis occurred, which helped the Curie temperature a little bit. And the reason why this curve looks the way it does is no dramatic insight. It's basically just sort of slowly and carefully, systematically getting better control of the growth conditions and all the sort of the grunt work of material science that makes things go. And so this 600 Kelvin Curie temperature is sort of more or less our current state of affairs for optimized material. There's some structure in M versus T, which I can talk about in a second. But if you just do a very crude analysis at room temperature, it's within 85% of its maximum magnetization. And extrapolating to extract TC is a little bit tricky because there's a low temperature magnetic phase here, which sort of limits our ability to fit reasonably to low temperature. So if you fit just this region to a Bloch law, you get an energy scale of about 600 Kelvin. You'll notice at room temperature, we have pretty sharp switching, we have pretty high remnants. It's pretty well saturated. In fact, this curve gets worse at low temperature, which is interesting. And I think that's connected to this sort of re-entrant phase here, where it becomes more disordered at low temperature, more anti-ferromagnetic. I think this is actually related to carrier freeze-out, coming back to, I think, really interesting and outstanding questions about how transport works here. Because I think that the presence of high temperature, at high temperature, of more delocalized carriers helps to stabilize and homogenize the magnetic phase throughout the film.
It goes up again.
Yeah, so I think this is probably dilute paramagnetic impurities in the film somewhere, at a guess.
But you're measuring magnetization, not susceptibility.
Well, it's in a finite field.
Okay.
It's in a 100 Gauss
okay.
field.
Yeah.
Yeah, I mean, it's very hard to measure just magnetization. Usually for a squid measurement, you apply a modest field to just get everything pointed in the same direction. So you're not, like in this case, we want to measure at a field high enough that we're not seeing weird domain well effects in the temperature dependence. We just want to be looking at the magnetization. Yeah.
How thick are the thin films?
Our typical growth is about 200 to 300 nanometers. We've grown as low as 50 nanometers and as thick as 10 microns.
Okay.
We haven't had any particular reason to make it thin. Making it thick makes some of the properties better, which I'll get to in a bit. Yeah, so this is sort of the state of affairs when we got involved with the field. Well, I guess I should say this data point is where we got involved. And we're looking for, oh, sorry, yeah, I forgot this slide was here. So this is just a cartoon version of the carrier delocalization argument that I was putting forth, where I think as the carriers become, if this green color you can think of as the length scale of an electron in the system, as it gets colder and it freezes out maybe to within a structural domain, then the film becomes more disordered, the net magnetization decreases, it becomes, one could say glacier, although I think that's formally not correct because there's still some local anisotropy within the grains. But qualitatively, that's probably a reasonable approximation, and then more uniform at high temperature.
What's ferromagnetic?
So this is a term some theorists coined for something that's almost a glass but has local anisotropy. So it's in the literature, so I mention it for that. Every 5th to 10th time I give this talk, there's someone in the back who gets very excited about spirimagnetism. And then there's usually some, and then the sign of the excitement flips. Oh, yes, that's exactly a spirimagnet. No, that's completely not what a spirimagnet is. It's just so that you know how sort of debates can get. But so in terms of what to call the phase, I'm agnostic. But in terms of the physics, we're in the process of trying to nail this down with more experiments. But I think qualitatively we have a lot of indirect evidence to support that something like that's happening. So then this was sort of the first experiment we got involved in 2011, which was sort of appropriate at the time for interest in spintronics. It was all about generating spin polarized charge current. So we made a LED structure and deposited a thin layer of ETCNE on the N-type electrode. Then driving current through the VTCNE layer acts as a spin filter. So you're injecting spin polarized carriers into this quantum well, and then by monitoring the polarization of the luminescence, of the electroluminescence, you can monitor the spin polarization of the electron current. And for detailed reasons that aren't probably worth going into, the heavy hole and the light hole give different polarization response. You can see here though in the heavy hole band that you get a polarization response in red that mimics in green the magnetization response of the film, so it acts as a spin injector. So we're excited about this result because this is the first time we believe that, anyone was able to demonstrate extracting a spin polarized current from an organic. So there is a reasonably active field of organic spintronics, but almost universally the organic in those structures, it acts as a channel rather than as the source of spin. And the other reason I included this slide was to show sort of how the Hannibal Lecter approach to sample fabrication that's sometimes necessary for air-sensitive materials. So this is a sample can that can go into our glove box. We can do metal deposition, some combination of pre-patterning and metal post, and then post.
Sorry, can you describe in more detail this Hannibal Lecter?
So this large square is the substrate covered in VTCNE.
Okay.
This narrow slot is the mesa of our LED. And then we deposit photoresist everywhere and open a window right above the mesa. So this black is VTCNE, which is deposited but irrelevant for the measurement. Then we put down a layer of aluminum because aluminum on VTCNE is a relatively happy deposition. But then the aluminum isn't as conductive as it could be, so we put on, as a final step, a little strip of gold here, an indium bond, which goes to feed-throughs out of this can. So this can has windows on it, so we can essentially seal it up in the glove box, take it down to our cryostat or spectromag, attach it to a stick, drop it down, and do the measurement. And so this is another reason why, in answer to Jeremy's question, maybe why this material hasn't been more popular, is that this is the kind of thing one had to do to do an experiment. Is you had to either come up with an experiment you can do in a glove box, or you had to come up with some, again, medium level of complication in terms of sample handling to get it into your apparatus.
So is that hermetically sealed with some O-ring?
Yeah, so it's got an indium ring, indium O-ring, because we wanted to make it cold. Yeah.
So what's it sensitive to? What's oxygen?
Oxygen.
Or both? Okay. And what's going to happen to the molecule? Remember,
the
we discussed
vanadium-
this earlier. I'm not a chemist, so I can't tell.
Well, I don't think I can give you a very sophisticated chemical
Okay.
answer, but the vanadium oxidizes is the bond.
So it is favorable for it to convert.
Yeah,
to
vanadium oxygen bonds are more stable than vanadium nitrogen bonds.
Will that pervade? That will go through the whole entire.
It does actually.
I
So
was gonna say you can have like a nice oxide layer to make a top gate then if you just.
if we were fortunate enough for it to
Yeah.
be self-limiting. So the material goes down as this blue-black color.
Uh-huh.
If you take it out of the glove box and put it on your desk, within half an hour it becomes transparent.
Okay. Medium oxide. Got it. Thank you.
You can with aluminum, which works reasonably well, but aluminum's a conductor, right? So not every experiment works for that. Well, to give away a punchline from a little later in the talk, what we've developed more recently is they make epoxies that we pirated from the OLED community that are specifically designed to not react to other organic molecules. And so by coating that with epoxy and then putting a top piece of glass or sapphire on top, we can stabilize it for the weeks to a month under ambient conditions. So this is one of the innovations we've been able to come up with in the last couple of years. So this was at the time, this was an interesting proof of principle. We were working with Art Epstein, who was one of the co-discoverers of the material. He's at OSU, and then right around just after this paper came out, Art retired, and so we had to make a decision about what we wanted to do. And in addition, We made a great spin LED, and I've published other papers with that technique. And I would be the first person to say spin LEDs are great for demonstrating physics, and as far as I can tell, completely useless for anything else. So there's not really like a worldwide drive to get more spin LEDs. And the field of inorganic spintronics, or spintronics more broadly, was moving away from this DC injection spin FET sort of picture and moving towards these dynamic excitations, which in some sense are maybe closer to what magnets and spin want to do naturally. So they have magnetic resonance in the gigahertz range, and by pumping those resonances, you can drive pure spin currents across interfaces from ferromagnets and the non-magnetic materials. So this was first demonstrated in inorganic magnetic systems. More recently, this has been shown for organics here, papers by Saito and Searinghouse, where this is maybe the easiest figure to see. This is the microwave absorption, tuning through the magnetic resonance of a permalloy layer. And they get a readout in the microvolt range of a transverse voltage coming from the inverse spin Hall effect. In principle, demonstrating spin injection. So these experiments, though, if anybody has looked into this field, are messy and hard to interpret. The shortest way to say it is that's a 1 microvolt signal in an FMR cavity where you're putting in hundreds of milliwatts of microwave radiation. So artifacts are a big problem, which is one of the reasons more recently I was very excited to see this collaboration out of the Bowman-Bernanke groups in Utah, where they did some very clever things in designing their microwave environment to effectively put an in parallel capacitor with their sample, which shorts out many of the artifacts, and they did some careful systematics. They also systematically varied the molecule to vary its spin-orbit coupling, and used the molecule itself as the spin Hall material. And so demonstrated, I think, very interesting spin pumping into an organic system. But just like my earlier comments about organic electronics, in all of these systems, the organic is playing a passive role. It's the channel for spin. And so this was an impetus for us to consider the microwave resonance properties of ETCEC. So the question became, can ETCEC act as the pump in these systems? And so this is really, to butcher a quote, the FMR spectrum that launched 1,000 ships. Right? So this is just from a commercial EPR spectrometer, and you can see the line width for this particular scan is a little bit longer, a little bit wider than 1 Gauss at 10 gigahertz, which is extremely sharp. And in fact, when we first saw it, the reason why there's this inset with control panel, or control measurements, is we looked at our 2 precursors to see if they were giving the same signal, because this looks like ESR. You just generally don't see FMR line widths that narrow. And so in the context of this new direction for spintronics writ large, we got very excited about the potential for this system. So to help calibrate for people who may not be as familiar with either this concept or just this units, right? Because there's many different ways one can represent the width of the resonance. Here's sort of a list of typical magnetic materials and the width of their magnetic resonance. And so magnetic metals are generally terrible. YIG has been the benchmark for decades, for 50 years or so. And in thin film, the very best samples grown at high temperature on GGG can give you a line width of about 1 Gauss or 1 Ørsted. If you take bulk single crystal YIG and polish it into a sphere, you can get down to about half that. This is now from one of our 10 micron thick VTCNE films. And the reason the thickness helps you here is there's magnon-magnon scattering that happens at interfaces. So it's generically true of all these materials that as you make them thinner, the line widths get broader. So having a bulk material can help your line width. So now we've taken that line width that was a little larger than a Gauss for the thinner films. For these thicker films, it's now getting close to the polished YIG microsphere, which is basically the gold standard for magnetic resonance. So this, coming back to Jeremy's very nice introduction, this is sort of why I think we have reason to claim that these materials are competitive with really the best magnetic materials out there. So,
What's going on with that spectrum? Why doesn't it come back?
so this is this is just a measurement artifact. So this is before I was showing you a derivative scan, which is how the data is measured.
Right.
So this is the integral of that.
Oh.
So any small
Right.
sort of
Any
slope
small
or weird offset in the background of the microwave response will show up. And that kind of stuff. So I'll just skip through this. This is basically just what I said earlier, that this is what happens if you leave an unprotected film out. If you protect it, it's good to the eye for a month. If you want to look at it a little bit more carefully, this is now log scale in hours. So this point here is about 2 weeks as a calibration. And so the remnants dies faster than other properties, but this is just measuring the DC magnetization, and depending on what you care about, you can get a few weeks to a month out of it. We have unpublished data with thick FMR films showing that they were good for similar timescales. So up to
So
about
are
a
these
month
just
long.
left in air?
Yep.
I see. But if
Just
you,
sitting on a
if you keep
desktop.
them in a dry nitrogen environment?
Yeah, if you keep them in a glove box, they last much longer, and if you keep them cold, they last forever. First time. Okay, so I took about half my time, but that's basically the introduction. So that's sort of laying the foundation for what these materials are, why we're interested in them, and sort of what the state of the art as N-1 or N-2 years was. So for the rest of the talk, and we'll just go as long as I have time for, and you guys feel free to ask questions. We can dynamically tune sort of what we're working on right now. So the first topic is just, even though we started off inspired by sort of this next generation spintronics concept, it turns out that just the parameters that we were getting were sufficiently good that we decided, well, there's much more, in some sense, vanilla, but still very impactful microwave electronics that we can do. And so the experiment here is basically just taking 2 microwave antennas and bridge them with a bar of ETCNE. And so the microwave field from this antenna will excite a spin wave in one end of this bar that then propagates to the other antenna and shows up as microwave transmission. So you can see here, this is sort of the real space image of what this looks like. This is a collaboration with Hong Teng's group at Yale and Michael Flatte's group at University of Iowa. And so that allows us to now do broadband FMR. And so you can see these very sharp resonances persist across a wide frequency range. The difference in amplitude here, still unpacking a little bit. I'm not sure, it's not clear yet if that's intrinsic to the VTCNE or just has to do with the measurement circuit being sort of better and worse coupled. But these Q of 3000 or 2000, depending on the different field orientation in plane and out of plane, are comparable to the 1 Gauss linewidth regime. And I'll show you the thicker films in a second. But because it's broadband, we can track and extract the gyromagnetic ratio and the saturation magnetization. And this matches what we see in DC and cavity FMR reasonably well. And so this is comparable to the 700 milliersted line width I showed earlier. And now you can start to see for a thick film, so this is now a 10 micron film, that we're seeing very distinct peaks, very clear spin wave resonances coming out of the broadband FMR. So this is, as I say in the last bullet, very competitive with YIG and demonstrates that you can make practical microwave devices. And so now this direction of research, we're sort of continuing our work with the TAN group to try and make more useful. I mean, this is sort of the microwave equivalent of a resistor. It's just connected to two antennas. We're trying to now move on to make filters and circulators and more sophisticated structures. So in a different direction, but one that has potential to circle back, we also have discovered really fascinating things about the morphology. So because this is a CVD deposition, it comes down conformally, and in collaboration with Georg Schmidt's group at University of Halle, we decided to try and make it corrugated, with the idea being that we would make a conformal film and then use the shape anisotropy of that corrugation to induce some in-plane magnetic anisotropy, just because the films as deposited have no in-plane anisotropy at all, and that's a degree of freedom we'd like to have. So the first time we did a deposition, we just threw it in the SEM, so some of this is oxidized, but we just wanted to see what we've done, and we were very surprised to see this. So what you see is some sort of ripening happening at the, well, it's not totally obvious from this picture, but from some diagnostic growths, it starts at the corners, that it deposits faster than on the edges, and then as these corners grow out, they start to shadow the trenches, and so then you're just depositing on top of the platform, and you end up, as you can see in these two different perspectives, with arrays of nanowires. And so that was very cool, we thought. So then we tried to look at the anisotropy, measuring DC magnetization, parallel and perpendicular. This is not really the best way to measure magnetic anisotropy. So we can see that those two curves are different, but extracting parameters from that is challenging. So what we did was we went back to FMR and we varied the in-plane angle. So that's this waterfall plot here. You can see this very clear sinusoidal oscillation, which we fit and extract here to the black data points. So for comparison, the open squares are for a continuous thin film. And so this variation in the center field is a measure of the strength of the anisotropy field. And this is comparable to the saturation magnetization. So this is a very large anisotropy for the material. And so that's not necessarily surprising because you're making wires, and wires are anisotropic, so one might expect we do some calculation for shape anisotropy. Magnetization perpendicular to the wire should be the same as different from magnetization along the wire. So we tried to do this by doing a thickness dependence, which you can see overlaid here, as well as varying the pitch of the array to vary their overlap. And as you can see, this is probably the most dramatic case. So this is a 1.4 micron film, so this is the black dots here. So the film's completely recoalesced. So if I was going to do a magnetostatic modeling of this, it would look like a thin film. From the top, you can still see ridges. So there's some sort of memory in the material of the fact that it started off as individual wires. If you look carefully, you can see sort of faint vertical striations here. So there's some sort of interface that persists even after it recoalesces. But as far as dipole fields are concerned, that doesn't matter. But the anisotropy is exactly the same as for well-isolated nanowires. So what this means is this anisotropy is in fact not shape anisotropy. And really there's only one candidate left, and that's some sort of crystal field anisotropy. So coming back to the very beginning of the talk when I was discussing the crystallinity or lack thereof of these systems, the only way we can be getting in-plane anisotropy out of this film is if there's some preferred molecular ordering. And that ordering is not there in a uniform thin film, deposited on a flat substrate. So something about these interfaces is templating some ordering. And so retroactively, coming back to the data I showed you at the very beginning of the talk, we can measure in-plane to out-of-plane anisotropy in thin films, which we assumed was just the shape effect. And I think that's there, that's part of it. But as part of that, we suspect there's also some surface templated anisotropy there as well. It just happens to be pointed in exactly the same direction as the shape anisotropy, so we had no idea it was there. So this is sort of giving us a lot of interesting food for thought. From an applications perspective, this now gives us the capability to grow different shapes with different anisotropies. You can imagine growing rings, spheres, and other things. If you want to get really exotic, this looks like a 1D magnon crystal. Those interfaces may do something to the propagation of spin waves, although we haven't done those experiments yet. So, and then sort of casting light all the way back on the fundamental questions of structure and property, the structure-function relationship of this magnetization. It seems like there is actually some order there, and it does do something. And we are trying to come up with creative tools to figure out how to get in there and find it. Yeah, sorry.
So this is really cool. So to me, this just looks like a stack of films on its side, like the equivalent
Yes.
of me putting like 100. I'm looking 200 nanometers down this way. But what you're saying is, it mattered that it started growing at the bottom and went this direction, instead of me laying it down like on a large, planar surface. So somehow it matters that it's like the growth field, like its next nearest neighbor is itself or something. You know what I'm trying to say? Somehow that
Yeah,
matters.
I think though it's, so from the way you framed it, I think it would be less surprising. So, well, no, never mind. So I was saying,
You know what
like,
I mean?
if you're
you
growing
turn that
steps.
90 degrees,
Yeah.
it looks like a stack of, you put down.
Yes,
10
so we could do it that
200
way, and actually I have some slides at the end where
Yeah.
we're making heterostructures.
But you don't see that. You don't see these problems.
Well, I think the problem there is that the signal we look for
Yeah.
to see whether that's happening,
Yeah.
at least in the magnetic properties, has exactly the same sign as
Oh.
the signal that you get from a larger
I
wave.
didn't understand that. So you can't decouple.
Exactly.
Okay, got it.
It's only by turning it sideways
Huh.
that we basically rotate this anisotropy by 90 degrees,
Yeah.
but we keep the film anisotropy still perpendicular to the bulk
I get it.
substrate.
That's
So as we sort of do this, then we see that, this still remains, but now we get this additional component
That's neat.
orthogonal. Right, so this then was happening simultaneously with another experiment aimed at anisotropy, or not aimed at it, but exhibiting anisotropy that was going on at the same time. So this is a related compound, vanadium METCEC. So the translation of that is you take a TCNE molecule and you replace one of the cyano groups with a carboxylic acid, or carboxyl group, excuse me. And so this changes the electronegativity, it changes the bulkiness or the steric nature of this ligand, and it removes one of these binding points for vanadium. So we initially did this, we're looking at this material as a way to tune the magnetic properties, but when looking at the temperature dependence, we looked at the magnetic resonance as we rotate from in plane to outer plane. And so at high temperature, this is exactly the shift in center frequency that you expect from this thin film magnetic anisotropy. So as you go to out of plane, sorry, this is in plane, this is out of plane. So as you go to out of plane, you need to apply, no, this is in plane. You need to apply less magnetic field. Sorry, there's a minus sign there that trips me up every time. But basically, the magnetic resonance is shifted by the demagnetizing field. It provides some additional field on top of the field provided by your magnet. And this shift is consistent with what you expect from a magnetic plane. But then when we cooled it down to 80K, we found, so the spectrum gets messy because this material is messier than BTCNE. That's a sort of a separate topic. But if you'll notice, this trend is now going in the opposite direction. And so if we just track those two behaviors at low temperature and high temperature, you get these phase flipped variations. So what this means is that we've been able now to switch the easy axis from out of plane to in plane. So coming back to the intuition we built up from this nanowire study, this means that we have, at high temperature, some easy axis in plane defined by shape anisotropy. But at low temperature, there's a transition, and we think this actually may be a structural phase transition in the material, where a crystal field anisotropy turns on with a different symmetry. So it pushes the easy axis from in plane to out of plane. And in fact, because it goes through 0, we can actually say the sign of this crystal field anisotropy is negative. And so in order to have a crystal field anisotropy, you have to have some crystalline order. So this is sort of further evidence that, and now this is not the in-plane rotation I was talking with nanowires. This is all in-plane to out-of-plane. And this is sort of another way at pulling out the degeneracy that I mentioned before. So with the nanowires, what we're doing is we're effectively rotating one of these anisotropies to in-plane so that we can detect it. Here, they're still both pointed in this direction at high temperature, and at low temperature, one of them flips. So it's another way to sort of break that degeneracy and see the evidence of this underlying order. And so we're still digging through this data set and trying to understand what we can extract from this, but this is sort of now not, who knows if this is ever useful from an application point of view, but in terms of understanding the fundamental magnetism, this is sort of a direction that we think is pretty interesting to move in. Okay, so I have one more topic. It's about 15 minutes left. Should I cut it and then open questions, or do you want me to just run through the last slides? What's the preferred mode here?
You're saying the last section is 15 minutes?
It's probably not. It's probably 5 or 10 minutes. Okay, I just wanted to check. This is sort of a more chemist's eye view of the material. So I mentioned, so this is the compound, the parent compound, vanadium TCNE. I talked in the last section about this METCEC, where we add this functional group. ETCEC, we basically make that functional group even more bulky and more electronegative. So the reason we had those films in the first place, this anisotropy discovery, was basically serendipity. But we're interested in looking at how does the magnetism change as we vary the ligand. So this is just structural characterization to make sure we're still making a compound. And so here's the comparison. Here's the magnetization of vanadium METCEC, the one that I was just talking about. And you can see some of the properties are similar. The magnetization actually looks sharper and better at high temperature than low temperature. The qualitative features of the M versus T are still the same. So it starts off in this ferromagnetic phase, and then at a similar temperature of 150 Kelvin, it turns over and starts dropping, although these effects are obviously much more pronounced in the METCEC. And the Curie temperature is now just a little bit above 300 Kelvin. So from the pessimist point of view, we didn't make the magnetism any better, we made it worse. The optimist would say we've now made the second best organic based magnetic material by taking the best and messing it up. But we had some bandwidth to work with, and so making the ligand more bulky and more electronegative, sort of, one way to say this is it's quenching the long range magnetism, sort of the robust long range magnetic ordering in the film. And then moving even further to this ETCEC ligand, you can see this is now only 150 Kelvin where the magnetic ordering kicks in. And depending on the field you apply, you can sort of anneal this out or see the same reentrant physics, which is pushed to lower temperature, because basically the Curie temperature has come from 600 Kelvin right onto this low temperature transition. And so one of the things that we can do moving among this set of materials is we can essentially show, this is some of the evidence I referred to in the beginning of the talk, that sort of the general level of order in the film, one of the things that will do, making the film more disordered and making deeper traps, will make it harder to delocalize carriers. And as those carriers become more and more localized, the Curie temperature becomes more and more suppressed. So we're sort of killing the long range order and left only with short range is one way to look at this data set. So then now just 2 slides of very speculative preliminary stuff. We can make heterostructures of this. So we can put, and so this is not VTCNE, but ETCEC for historical reasons. We were, as usual, making the sample for other means or other reasons, but putting it on top of YIG. And then you can play a trick where you vary the in-plane angle. And YIG has a larger magnetization, so it will tune much more broadly as you vary the angle. And so we can walk the frequency of the YIG resonance directly on top of the frequency of the organic resonance. And when we do that, you can see the line shape changes dramatically. So these peaks, these additional peaks from the organic disappear, and the resonance, at least this half of the resonance, sharpens up. And so this is a very clear signature of resonant coupling between the two magnetizations. So we're still working on disentangling whether this is dipole-dipole coupling or exchange coupling. Dipole
How
would
do
be,
you know that it's coupled together? Because, I mean, it just looks like they could be superimposed.
well, I mean, they can't, is the short answer. So if you sort of clip, this part of the graph and just numerically add it to that part of the graph, I mean, you can tell sort of just by seeing the amplitude of this compared to this. Right? If you just superimpose these two resonances, it gets lumpy.
But at 40 degrees, those features are gone anyway.
Well, I think they're starting to share oscillator amplitude. So I think so this is basically, I think, a generic effect if you have two coupled oscillators, right? As they couple, you get a common mode. And I think this is what's happening here. And so you can see there's a kink in the line width at about that field. So I won't say that this one plot is enough evidence to definitively say that this is happening. That's a fair statement. But it's pointing to some interesting potential. And then, yeah, and then we're done. So this is sort of the summary. I've just said all of this. It's late in the afternoon, so I'll just leave up slide references. Let's look at that and thank everybody for their time.
Time for questions?
So electrically, this is a semiconductor? We didn't get
Yeah.
to this earlier. So what's the band gap of this stuff?
Well, so this is sort of what I was saying about decades in temperature and whatnot.
Yeah.
So if you choose to plot it on an Arrhenius plot,
Uh-huh.
then you get an activation energy of about a half an eV. I'm not quite sure whether to call that a band gap. Because for a hopping conductor, that activation energy means something different. And so this may be my personal ignorance, but I don't think certainly for this material, the field hasn't really addressed that question yet. So if people have suggestions on ways to sort out that distinction with some measurements, would be very interested in hearing about them or collaborating for them. That's the best approximation, best way to answer that.
So what about 2D patterning, magnonic band structure,
Mhm.
materials? I mean, what have you taken a stab in that direction, or?
That's in process. So rather than making ridges, you can imagine making little pillars of various lattices. We have effectively done that with pillars of YIG, and we get a spectrum with extra lines that are moving around, and so we're in the process of sort of trying to understand exactly what those lines are. And although that was more in the spirit of a sample we happen to have, so it's not necessarily in a sort of carefully tailored magnonic crystal structure. But yeah, that's a direction we're aggressively interested in moving in. And so we also have some hope that we may be able to pattern using traditional lithography. So one of the other pieces of received wisdom that we got from the prior field was that this material, you can't see any solvents, which makes traditional processing challenging. But it turns out in the synthesis, there's dichloromethane used at one stage. And so we just tried soaking the films in dichloromethane after they're deposited, and it turns out they're fine. And in principle, that will remove PMMA. So we're basically, well, hopefully my students back in Columbus right now are sort of depositing and doing
You
some
just check your
liftoff
iPhone
and trying
and
to
see
yeah, we can
for
call
an
them and
update.
find out, yeah. But so that's another way to think of patterning that sort of magnonic crystal. I think the really exciting thing is that there's the potential to do that patterning without interfaces, so without the edge damage that you get from ion milling or sort of other etching techniques.
Is there any way that you can add more carriers to the system by proximity or?
Yeah, so we've thought pretty hard about that. We've tried a couple of different approaches to doping, sort of co-depositing with other molecules. None of those have really panned out. I mean, one of the challenges, as we discovered in this process, is that one person's doping is another person's molecule out-competing your desired precursors for the right bonding arrangement. But so we've tried that. Art Epstein tried some electronic gating and didn't see anything, but I wasn't part of those experiments. I'm not sure exactly, I'm not sure how that was done and whether that's really a no. Some solid electrolyte gating to really gate the heck out of it might be interesting if we can come up with a way of doing that without melting the material.
Well, not only that, but this solvent issue, if they're sensitive to polar solvents,
Yeah.
then depositing the electrolyte is a challenge.
Yeah,
But we have a material we're working on has exactly the same problem. We do everything with low box, well, so we can talk about that after this is over.
Sure.
How we're trying to get around that issue
yeah.
to gate. So it's really almost backgated though, right?
Yeah, well, that's the earlier work.
Yeah, but
And
not great gate
I
control.
I don't know what they tried, how they tried it. And then it's not a trivial question how to read it out either. So we don't see, for example, an anomalous Hall effect because the mobility is very low. So we would probably need to do some sort of magnetization measurement on the as-gated material to see if it's affecting the magnetization. So that's not impossible, but that's just a little bit tricky figuring out how to actually do that experiment.
So clearly this material is as good as YIG, and it seems like from your, and it has the ability to be like deposited in funny
Yes.
geometries. So what are some of like, wild, things that one could do with this that you couldn't do with YIG?
Well, I think, for example, this Magnon crystal idea is one where we have the potential to have much higher fidelity Magnon crystals than for YIG. So I think it's always dangerous to chase an established technology. And so, for example, our collaborators at Yale have been working at depositing and recrystallizing. So depositing patterned YIG and then recrystallizing it on the substrate to get some nice single crystal material. And I know at least one other group that's doing that. But generally, the quality of the YIG that you deposit that way is not as good as the thin films that we're already beating. So my guess is that they would have more damping. And so that's probably the right way to say it. So crazier than that.
I guess my question is these non-reciprocal devices that people are always trying to do with YIG, right?
Like circulators?
Yeah, circulators.
Oh yeah, so this is what I sort of mentioned in passing when I showed the work with Yale with the two antennas.
Yeah.
We just got funding to do exactly that, to try to build a circulator, swapping in VTCD for YIG and seeing what the response is. And so we're ramping up. I just hired a postdoc. We'll be starting in February to hopefully get that going.
So, in line of crazy devices, in the field of these topological devices, there is a constant need for flexible, patternable, ferromagnetic insulators, or maybe ferromagnetic semiconductors.
To put on top of topological materials?
Yeah, yeah. So if it's a ferromagnetic metal, then those electrons poison the
Yeah.
topological state. So
But
but most ferromagnetic insulators are difficult to process into devices.
yeah, I'd be very interested in doing something like that. So, yeah, if
There's a
if
question of
anybody-
how thin can you make it?
How thin? Well, so the thinnest we've deposited is 40 or 50 nanometers.
What happens below that? Don't
We
know.
just haven't tried. So yeah, we haven't really explored the thin film regime too strongly, so I don't know if there's like a nucleation layer or not.
Or dead layer?
Or dead, no, maybe even a dead layer, yeah. But in the literature, there had actually Art Epstein's group did successfully deposit with MLD, sort of layer by layer deposition, and they
Okay.
got that to work.
This same material?
Yeah, the vanadium TCNE.
Okay.
Without the water activation, not like alumina, MLD, but sort of a layer of TCNE, and then a layer of VCO6, a layer of TCNE, a layer of VCO6. And they used the quartz balance to try and calibrate. So, I think that was one paper.
Okay. So it was hard to do, but maybe
So
it demonstrates that you can make very thin films
that
potentially.
seems to suggest. We've also tried just because TCNE is actually relatively well-behaved molecule, easy to evaporate. So I tried putting that into a thermal evaporator, organics thermal evaporator, and just depositing a thin layer of TCNE, and then putting it in the furnace with only VCO6. And he got VTCNE. It was not this quality. It was much messier FMR spectrum, but that was a couple of attempts. So just kind of to play around and see what we can do. I would say we just really hadn't had a compelling reason to try and make super thin films at this point. But if there's a good motivation to do that, then that's definitely something we could explore.
Yeah, maybe it's interesting to study the proximity effect between this kind of material and some semiconductor, graphene, or more traditional.
Yeah, so that we are doing. We're sort of collaborating with the Kawakami group to put VTC on top of graphene exactly and look for an anomalous Hall effect.
See anything yet?
Not yet. Not yet. Although that's mainly because the first sample didn't survive into the cryostat.
Okay.
We'll just say it at that level. New graduate student getting used to the technique.
This is through the MERSEC?
Yeah. So that's part of our 2D materials hierarchy. So this work is not funded through MERSEC. They're allowed to collaborate.
Okay, let's thank Zeke again.
Thank you.